Rosetta and Philae are a pair of spacecraft created by the European Space Agency and launched in 2004 to create the most extensive study of a comet that has been attempted to date. This project was conceived in the early 90s following the launch of a comet flyby mission by NASA. The launch, which occurred in March of 2004, was successful. Originally, it had planned to launch in 2003, but was delayed following a similar probe's failure. Rosetta represents the larger satellite spacecraft, while Philae was designed to detach from Rosetta and land on its target. The Philae lander was meant to use its own onboard instrumentation to study the comet's nucleus from its surface. It was meant to use its harpoons in order to attach to the comet's surface and then utilize thrusters to ensure a bounce-free landing. However, there was a problem, and both the thrusters and the harpoons failed to activate correctly, making Philae bounce multiple times while attempting to land. Despite this, it managed not to escape from the comet, now referred to as 67P for short, and has stayed stationary. However, due to suboptimal landing conditions, Philae's power supply has dwindled, and it had to place itself in standby mode to conserve power. Recently, has since come out of hibernation and begun infrequently transmitting data to Rosetta. Philae and Rosetta both have instrumentation that was meant to work together in order to understand certain properties of 67P. For risk and reliability analysis, this means that the two spacecraft working together provides a complex network of interdependent systems where failure in one system can reduce another system's usefulness without rendering that system completely useless. Due to the nature of space exploration and comet exploration in particular, the potential failure modes of this project have the potential to be very extensive. The focus of this risk analysis will primarily be on the particulars of Philae and Rosetta's regular operation, that is to say, their continued collection and transmission of scientific data as they operate on comet 67P, as well as the particulars of Philae's landing. The primary reasons for focusing the project to this particular segment of the Rosetta-Philae comet project are scope as well as variance in the risk analysis itself. The primary aerospace component of Rosetta's launch is already in the distant past. It was, by all standards, a success on its own. Doing a risk and reliability analysis on this part of the project is then, by its very nature, particularly redundant. Furthermore, risk and reliability analysis on the rockets that launch these spacecraft would pose a threat of creating a sort of system creep. The launch of Rosetta would bring with it its own set of complex subsystems, which would create the danger of sectioning off too much ground to cover over the course of a semester-long project. Conversely, focusing on Philae's landing on the nucleus of 67P would still be worthwhile due to the relatively untested nature of what is being attempted. Philae's mission is essentially one of a kind. Focusing more on Philae's current operation provides the opportunity to give greater focus towards problems more associated with robotics and automations, such as how autonomously detaching a lander and sending it to the surface of a comet might go wrong, as well as exploring how the latency between Earth and 67P complicates the mission by introducing the need for automation. Let's go into some description and some detail about the subsystems at play. Rosetta is the one we'll be covering first. Rosetta is the designation given to the EXA spacecraft currently orbiting the comet 67P, which is collecting and transmitting data to Earth after having deployed the Philae lander. It follows a general satellite bus design, which houses both the Philae lander and the scientific instruments for its data collection task. It is powered primarily by its large solar panels, which have 640 square meters of area. Power is controlled by a redundant module and stored in nickel-cadmium batteries. As such, power represents three components, with the solar array being divisible into 10 separate solar panels. Rosetta contains both a high-gain and medium-gain antenna for transmission and reception, which represents a redundant system in case of emergency with Rosetta's operation. Beyond these communication subsystems, there are two more low-gain antennae, which are omnidirectional. This represents a quadruple redundancy in Rosetta's communication suite and provides 4 components for analysis at minimum. In order to complete its mission, Rosetta has 11 different scientific instruments that it can utilize to measure parts of the comet nucleus it orbits, as well as its gas and particulate interactions and solar wind interactions. Exploring each of these subsystems in depth provides an opportunity to model complex systems interactions, especially given their connection to the communication system. Beyond that, Rosetta has 2 subsystems related to propulsion, 3 if counting the connections between the 2. Namely, it has the titanium tanks that store the liquid fuel it uses, as well as its thrusters. While these would be of minor importance to the project relative to the rest of the system, given the current scope, if Rosetta needs to make frequent or semi-frequent course corrections as it orbits the comet's nucleus, it would still be relevant to the interests of its day-to-day operations. Lastly, the bus system and heating systems provide 2 more potential components to take into account. These systems support the continuous operation and structural integrity of the spacecraft as a whole, so risk and reliability on them provides insight into the largest potential failures that Rosetta could encounter. Philae could also be considered as a subsystem for Rosetta, as it was carried by the larger spacecraft for the length of the journey. However, this does not directly connect to the functioning of the spacecraft from day to day. In total, that means that Rosetta provides this project with 21 individual components at a minimum. Now, we shall discuss the Philae lander. The Philae lander, by comparison, has 11 separate components to take into account that are not part of its scientific payload. These include its power system, the heating system used by the lander, the harpoon gun which failed to anchor it to the surface of the comet, the thruster it failed to use to decelerate its landing, its communication system, the telecommunication system that it used, and its landing system. With all these components being exposed to different conditions from Rosetta, and being designed to overcome different situations, namely the impact of landing on a comet combined with the task of not falling off, the project offers a number of different failure types to explore. Another major subsystem of Philae's, like Rosetta's, is its science instrumentation. There are 10 individual components to Philae's science payload, each accomplishing individual tasks on the surface of the comet. This science payload consists of systems that range in diversity from X-ray detectors to panoramic cameras. Studying the potential modes of failure or potential methods to improve redundancy provides a large swath of possible modes of inquiry. One crucial note about Philae worth noting is that several of its subsystems failed concurrently when they were supposed to work together, and as a result it landed in a suboptimal pattern that sent it into standby mode. Because of this, Philae provides a strong impetus to ask how its systems could have functioned better, while providing several starting points for risk and reliability analysis. The fact that Philae is still operating, even on standby mode, only adds to the potential complexity and depth of analysis possible on the lander. However, Philae and Rosetta are not the only subsystems that are regularly used as part of its day-to-day operations. Here on Earth, there is another crucial subsystem to consider as part of the regular operation of Philae and Rosetta. In particular, this subsystem represents the connection between the lander probe pair and Earth itself. Instructions are sent to Rosetta from the European Space Operations Center located in Germany. With that in mind, it might be beneficial to look at possible modes of failure that could occur here on Earth that might result in the loss of valuable data or perhaps even damage to the probe caused through poor instructions. That concludes the subsystem and component overview of the Philae and Rosetta spacecraft. Thanks to the unique nature of the mission and the unique nature of the spacecraft involved, a risk and reliability analysis of Philae and Rosetta subsystems is sure to provide insight that could be used in the planning and design for other comet exploration projects. Hopefully, this video proved enlightening in explaining the overall workings of this complicated spacecraft duo.